OEIS is a role model for future mathematics.
Do I need the microphone? Can I just talk loud? On behalf of Sarah and myself, thank you very much for having us here, and we wish Neil a very happy birthday. It's a wonderful occasion to see everybody, to meet people. And we'd like to talk to you about something that's near and dear to our hearts, and I think near and dear to the hearts of many people in this room. And that is the idea of fingerprint databases, or fingerprinting mathematics, or encoding mathematics, and there are many, many ways to think of this. But we call it fingerprinting. So let me give you a little bit of a background here. If I can get this to work. Here we go. What is a mathematical fingerprint? So you probably have an idea of your own fingerprints. And we use that as a model to talk about mathematical fingerprints. So let me give you an example. Here's a sequence of numbers. It appears in the OEIS, absolutely. And I'm going to call this a fingerprint. But what does that mean? Well, it's a unique identifier. It's a way of describing some object or some class of objects. And in fact, it's a way of this particular identifier can be associated with several different classes of objects, as you might suspect. And here's one. So the nth term in this list enumerates the subsets of 1 through n minus 2 that contain no consecutive integers. Okay, so you can prove that if you'd like. Another thing that this sequence enumerates, so the nth term in this sequence also enumerates domino tilings of a rectangle of these dimensions. Okay. So here are some, there we go, here's some mathematical objects, and they can be identified by this sequence. So we want to talk about mathematical fingerprints. Again, we're kind of having this fingerprint in mind. And what are the properties of a mathematical fingerprint? Well, I'm just going to do this. I want it to be small. Like this is small. Somehow I want this to be small. I want it to be canonical in some sense. And I want it to be language independent. We heard this nice introduction of all the people who are kind of the godfathers and godmothers of the OEIS, and they're coming from all over the world, and our collaborators are all over the world, and I don't want to have to translate the thing I'm talking about. I want a really clear and understandable way to explain the object I'm talking about, and I want that to be true of my fingerprints. One example of how to do this is to make it numerical. And as we're going to see, and this is going to sort of shift in our talk, is that the examples of fingerprint databases that we have are almost entirely numerical, and we would like to expand that in a certain direction. So I should really explain what we do with mathematical fingerprints. Well, we start by cataloging them in a searchable fingerprint database. So your image of the OEIS is sort of your canonical example here. And again, this is building off of fingerprints. The next thing you do is when you come up with something interesting that you can fingerprint in this way, you look for that item in the database. You query the database, you say, knock knock, is this guy inside? And based on the results you get, you use that to solve mathematical problems. Maybe your guy was not already inside, and so you have something brand new to bring to the table. Or maybe that fingerprint was in there, but under a different guise, and perhaps you can find some way that your object and that guy's were the same, or isomorphic, or however you want to call it. So for example, if you said, what is the relationship between subsets of this set containing no consecutive integers and domino tilings of this rectangle? Well, we saw they had the same fingerprint, so we can certainly say that those objects are in bijection with each other, and you can then work to come up with that bijection and use experimental mathematics to build on this and do all kinds of great things. Okay, so that's the very basic idea of a mathematical fingerprint. Now, what is a fingerprint database for theorems? Why bother? That's a good start. I mean, who likes to do too much work? Okay, we do. But let's be fair. So why should we bother? So let's say you have a mathematician M, and M has just proven a theorem, theorem T. can determine if a result is truly new, or if this theorem or some equivalent reformulation of it already exists in the literature. We've been there. We've suffered from this, probably. But this is something you want to do. You've already done some literature search, but you should expand it and check, is your result already known? And that's hard. That's really hard. Wouldn't it be great if M could encode T in some small, canonical, language-independent way, and then search for that encoding in a database? So if you prove a result and your result involves a sequence of integers, you automatically go to the OEIS and you see if it's in there. And if it's not, then you're off to a really great start. Now, what does it mean to be in there? How does the database encode theorems? Well, in addition to the fingerprint, I wanted to have other fields in the entry. So I wanted to list, and these are approximate names, but names, comments, formula, references. I want as filled out a database entry as I can. So each entry in the database could be a theorem or a collection of theorems associated to that particular fingerprint. So associated to 0, 1, 1, 2, 3, 5, 8, 13, and so on is this whole list of information. I'm going to call that a theorem. All of these things are tagged by this sequence. So what should a fingerprint database for theorems be? What properties should it have? And I'm going to think, I'm sort of guided by the OEIS, but I'm trying not to be blinded by it either. I want to think very generally. What properties do I want? It should be language independent. So canonical, no special vocabulary or notation. Maybe numerical. A lot of what we work with already is based on numerical fingerprints, but maybe we could be more general than that. It should be full of references, as full as possible. Literature, cross-references among databases. If you have code, put them in there. If there are links to things online, put all that in there. It should be collaborative. That's obvious, meaning open and accessible. This one's my favorite. It should be optimistic. Because false positives should be okay, but I don't want false negatives. So if I look up a fingerprint, well, it's not going to give me the whole picture of the result. Maybe I entered the first 20 terms of my sequence, and it gave me 300 entries in the OEIS. So it gave me a lot of false positives, and I'll then sort of weed through them and find the right thing. So these are properties I want in a fingerprint database for theorems. And the fingerprints themselves, again, should be small, canonical, and language independent. So what are some good mathematical fingerprints? So think about your own work, think about what brings us here today. Well, integer sequences are a great mathematical fingerprint. And hey, we have a database. So here's a page, okay? And we know these pages well, whether you're looking at your smartphone, squinting at it, or if you're looking at a big screen. There are lots of fields. Some of them are more filled out than others for various sequences, but this is a great resource. What else? Permutation patterns. So in, I think it was 2005, Sarah and I started talking about all the results that were out there for phenomena characterized by pattern avoidance. And after that, the database of permutation pattern avoidance was born. And here's a page from it. So again, very much modeled on the OEIS, linking, in fact, to the OEIS whenever relevant, and trying to keep track of various phenomena that fall into this category. One more. Statistics for combinatorial objects. So this is FindStat, or findstat.org. This is another searchable database of mathematical fingerprints. Now, what's close? So those are some existing mathematical fingerprint databases, and then there are a lot of other things that are really, really close to being what we have in mind. And I'm going to give you a list here, and a lot of the time, the reason something is on this list and not on a previous page is that it's hard to search through. Somehow, the infrastructure is there, and a lot of the information is filled out, but it's hard to just go query something. But otherwise, they're very close. So finite simple groups. Well, we have the atlas. That's pretty close to being a database. Dedekind eta function identities. This is Somos' collection. Smooth projected irreducible curves of genus G over fields of Q elements. This is many points. Hypergeometric series in canonical form. WZ method and the digital library of mathematical functions. And maybe some other things too. So in other words, what I'm listing here are things that you hopefully can understand and appreciate have these canonical language-free identifiers. And those things are ripe for a fingerprint database. So what else can one of these objects do, one of these fingerprint databases for theorems? Besides indicating whether a result is known, a fingerprint database for theorems can make unexpected connections between fields. So if you look something up and find the entry exists, but with an entirely different description, then hey, maybe you know something new. It can build on known results in this way and in others. It can yield new results once you figure out how to connect your brand new characterization with this one that's already in there. It can nurture mathematical experimentation. I like this one. It can improve the refereeing process. So there are a lot of broad benefits to these databases. So here's a goal. Let's dream really big. I want a universal database of all known mathematical theorems, formulas, algorithms, and so on. That would be great. You have 2 days. I would like it to be easily searchable. I would like it to be independent of language and specialized notation. Notation is a big problem, I think. In your own work, you come up with the thing, but it's not the same as what somebody else used. It's hard. I want it to be accessible to all. Now, so that's my goal, but let's be realistic. So that dream is far off. For one thing, it's hard to find a theorem in a foreign language. Formulas are hard to find via web search. Notation and vocabulary differ wildly and widely across fields. So this is a tough thing. So let's have a little roadmap here. So it's Neil's birthday, and we want to celebrate. And birthday presents you might accept, and I suspect a major one would be support of the OEIS Foundation. And so after you've done that, contribute to existing fingerprint databases for theorems. That includes the OEIS and all the other things I've listed and all the other things I haven't listed. Identify methods to fingerprint theorems in your own area. Create new databases for theorems by collecting and fingerprinting known theorems and sharing them with the world. And now let's get to the future, which is Sarah.
So I like Bridget's introduction a lot, and we're all warmed up for what can we do next. So I wanted to talk about 2 very concrete things that we can do to generalize and expand on the OEIS. So you're exactly the right audience for this. So the first one is, how can we make the impact of the OEIS and all the other fingerprint databases for theorems more relevant on a day-to-day basis? And the other one I want to talk about is what I see as a new frontier in terms of fingerprinting, and that's how to use pictures for labeling theorems. So, okay, so the first question I have to say is thanks to Michael Somos, because in an early draft of our paper, he rebuked us for a statement that we made. We had said that every entry in the OEIS characterizes a theorem. And this was maybe an exaggeration, but it was based on our experience. You know, when we go to look up a sequence, it almost always leads to something, or the sequence isn't there, and we put in our theorem. Right? So either way, eventually, that sequence gets associated to this theorem. And so we didn't think we were wrong, but we had to figure out where is he coming from? Well, so to explain this, think about the pages that you've seen. The one that Bridget's already shown is the number of partitions. I want to come back to that one because I think that one has lots of theorems in it. But here's an example of another entry in the OEIS. So this is the inverse of the 1,672nd cyclotomic polynomial. Do you see a theorem in there? What's the theorem associated to this entry? It's a little void, this one. This one's a little bit of a shell. It's not that there's no theorem, we just don't know what it is yet. And that's okay. But we had to figure out a way to devise a test. Is Michael right? Or are we right? Who's right here? And what is the probability of an entry in the OEIS really encoding a theorem right now? So the test was, sort of readily available to us because there's all these handy features. And I don't know if you've played with this one, but well, here's the entry for partitions. As I scroll down to get to the feature, take a look. Does this one encode any theorems? Convince yourself. It's the number of partitions. It's also the number of irreducible representations of Sn. Is that a theorem? Not really. That's just another way of looking at it, right? But it might connect you to another part of the literature. And as you go down, you'll see there are lots of things, lots of references on this. This is a huge entry. Lots of references pointing you to the literature. Then there's generating functions, recurrence relations, and the Hardy-Ramanujan formula. So this really is pointing you to lots of theorems in this case. Down here at the very bottom of the page is this cool way to access the OEIS, which I don't know if you've tried before. You see, you can browse the sequences. And looking at best sequences is lots of fun. But I had to do something different. I had to look at all sequences to get an idea if Michael Somos is right. And how often is it true that an entry encodes a theorem? So let's let it run here on 5-second intervals. And just yell out if you think this is a yes or no. Looks like a no. Maybe no. You with me? No? No. No. Oh, maybe. Okay, maybe. Yeah. But maybe a no here, right? Well, I'm not even, it doesn't even just have to be references. If it had a generating function, I would say that's a theorem. If it had a recurrence relation that's not obvious, that would be a theorem. So, when I looked at it this way, I had to say Michael was right. That a lot of these are theorems waiting to happen. Are entries that need a theorem associated to them, hopefully someday. So in my little random experiment, I very carefully went through 20, and I found 6 encoded theorems, so about 30%. And
you're ignoring the numbers. Like your example of the cyclotomic polynomial, you could say that shows there are no 2. There's no 2 coefficient of 2 in the first 50 terms.
So that's an
Every one of those
observation
things tells you something about the numbers in the sequence.
Absolutely.
All those numbers
don't confuse this for a criticism. I have a point that I would like to get to. And so there's so much there. And in fact, the key idea here is that it is important for you to add your references. So if you find an entry, you're doing some work, you come across an entry and it's one of these shells, later on you use it for something, it's really important for you to add that reference to the literature. And here's one actually right here, where I went and added my reference. This was a shell, and it has led to 4 papers of mine plus 2 others of other people because it was in the database. It was the beginning of a theorem. It was the beginning of a conversation that I had with somebody that's led to a lot of other things. And I have to say, it took me about a year to add that reference there. Why did it take me so long? I know I should do it, but this is why I'm preaching to you guys, because I know you're converted, right? You're already willing to do this. But let's see what we can do to enhance the OEIS as a fingerprint database for theorems now that we're thinking about it in this new way. Is that be okay with that, Neil? Okay. So, and same thing with these other databases, Bridget's database of permutation patterns or FindStat or whatever we'll eventually add up to. Okay, so that was my pitch on that front. Now let me switch gears a little bit and talk about pictures. How can we fingerprint theorems with pictures? So one premise that we generally all have is that currently, given our computer technology, humans are better at recognizing mathematically inspired pictures than and saying what theorem is related to that than computers would be. Is that right? Do you agree with that? Or some people protesting? Anyone protesting yet? Oh, yeah. Thanks. Okay, so let's test your skills, okay? This is a lot like showing you the beginning of a sequence and ask you what's the next term. So I'm going to show you a picture and ask you what theorem it goes with. See how good you are. You know the theorem that goes with this picture? Kuratowski's theorem, right? You should see this picture and say, oh, I know, planar graphs. Right, Kuratowski's theorem says that planar graphs are completely characterized by having no subdivision, which is isomorphic to K5 or K3. Great. What about this one? Let's play again. Do you know what theorem goes with this picture? I was hoping the author of the theorem would. So this is the Peterson family of graphs. They're drawn a little funny. The bottom one is the Peterson graph. And these are very special. These completely characterize the linklessly embeddable graphs in R3. So that means two cycles never interlock like this. There is some way to draw it in R3, so no two cycles interlock. And it's a complete characterization in the sense that if you avoid these graphs as a minor, then you have a linklessly embeddable graph. Okay, so this brings up a really important whole family of theorems that are coming up. And one of the theorems I consider the most important development in graph theory in the 20th century is the graph minor theorem, due to Robertson and Seymour. And it says that every family of graphs that's closed undertaking minors is always characterizable by a finite list of forbidden minors. Right, so it generalizes Kuratowski's theorem. It's a beautiful, beautiful theorem. It took 500 plus pages to write, spanned over many years. It's a big effort. And so every new theorem that comes up, every new family of graphs that's closed under minors could be characterized by the finite set and therefore a picture. So I wish this could be turned into a fingerprint database for theorems, something I'd love to see happen. And as I was kind of poking around looking for pictures on the web for this talk, I came across a curious family of graphs. These are called Y delta Y reducible graphs. They're relatively simple. It's any graph that can be reduced by 6 steps to isolated vertices. So you can remove a loop, you can remove a degree 1 vertex, you can convert a multiple edge to a single edge, you can replace a degree 2 vertex along some edge, you just erase that vertex and leave it just one edge. And then you can replace any triangle with an extra vertex in the middle and make it into a Y shape, or you can take a Y and make it into a triangle. Okay? So you do this in all possible ways, and if the graph can be reduced to isolated vertices, it's Y delta Y reducible. So Trumper showed in 1989 that this class of graphs is minor closed. So it's going to be characterizable by a finite set. How many graphs do you think are in the finite set? Anyone want to take a stab? That's a good guess. It's more than that, though. Turns out that Yang and Yu showed there are at least 68 billion graphs among the minimal set of forbidden minors, and they don't know if this is all of them or not. So there's still some work to be done here. But here's a case where in my fingerprint database for theorems, for us to include 68 billion graphs, it's going to take a fair amount of encoding in space. Is that something that we want to do? I don't know. There are limitations, right? I just thought I should point it out there that finite is still can be a large number. Okay, well, what about this one? Here's a whole different direction than graph minor theorem. Here's a picture that I've been staring at a lot lately, because somebody recently came to my office, and just like with the OEIS entry that I have to credit for so many papers, he brought me a post-it and said, is this interval and interval in Bruja order for some Coxeter group? And I had to say, well, it's plausible, it doesn't fail any tests that I know, but I don't know for sure. But I know that it's not an interval in a finite Coxeter group, because I know this picture right here. Does anyone else know this picture now that I've given you some hints? Yeah? So this is a picture that comes up in Axel Holtmann's work, and he has completely characterized every rank 4 interval in Coxeter order, but in Bukhara order for Coxeter groups, but only for the finite groups, because he can take a computer and run through the whole list of them and look at every length 4 interval. So I just recently re-derived this picture just to check, actually, it's computer proof. And the way you're supposed to interpret each of these pictures as an interval and a coset is that you think of the face as. So it has the empty face and then all the vertices and then the edges which contain the vertices and so on. Okay, so there's a picture that encodes a theorem completely, right? Well, those were planar graphs, notice too. So really everything I've talked about so far is planar graphs. So we could ask the question then, what is the right fingerprint for graphs? How should I represent graphs in a small, canonical, language-free, optimistic way? Have you thought about it? I mean, even for, the Peterson graphs, let's say, I sort of started to do this, and I was putting in the Peterson graph. So the first thing I tried was the adjacency matrices. That sounds like it's numerical, right? It's not exactly small, but it's squared. It's not that bad. But it has a problem that it's not canonical, right? I could put in the adjacency matrix, but you would look at the same graphs and probably come up with something different. So I have to think about isomorphism classes, really, and how would I pick one canonical representative for each isomorphism class of graphs? Well, what's the problem with that?
Graph isomorphism?
Graph isomorphism is a well-known hard problem, right? And we don't even know if it's anything complete. We don't really know how hard it is. But it's not going to be easy, and we want it to be a small, easily computable function. So then I came up with something that I could compute, which is degree sequences. What if I just put in the degree sequences of all of the graphs that I have in my collection? So it's a multi-set of degree sequences. Would this work? What's the problem with that? It's not canonical. Right. We can have multiple graphs with the same degree sequence. But maybe that's okay in the sense that maybe theorems about graphs are kind of rare. And so maybe I wouldn't have too many false positives if we use the multi-set of degree sequences. And that would be okay also, in the same sense that if you put in just 5 entries, 5 terms into the OEIS, you usually get close to what you're looking for, right? So maybe it would be a good approximation. And it is small, canonical, and language-free. But if you start doing it for the Peterson graph, that's one thing. If you start doing it for 68 billion, this is still a long thing. So what else could we use? What is the data that I have on hand? When I tried to enter this for the Peterson graph, I got bored pretty fast somehow. So what I have on hand usually is a picture. I have a picture of the graphs that I have in mind. And as I look around in the real world, outside of math, I see a lot of recent successes in terms of understanding pictures. So I don't know if you've tried this, but if you Google search for any noun, you put in cars, let's say, and you click on images, what do you think it gives you back? Really good at finding you 1,000 pictures of cars. And if I put in origami, because I need to get something for some slides that I'm making, and I put in images, I get back lots of great origami for them. Skill, I usually attribute to where I got them, but you can get lots of images. I recently was playing around with this for the talk, and I put in math to see what would happen, and clicked images. What do you think you get on that? So this K-12 idea is really good because it's all just elementary school math stuff. So there's a lot of interest in that, I would say. But also facial recognition is amazing. Facebook takes a picture that comes up, and it starts labeling my friends for me. How does it know that that's Joe and Judith and whoever it is? It's pretty amazing. And then the other thing I've seen recently is the Amazon product search, where you take a picture of an item you want to buy, and you put it into the app, and it takes you to that page in Amazon so you can buy it. Right? So computers are getting really good at recognizing pictures. So we have to ask the question again, then, are humans much better than computers at recognizing pictures and identifying the related theorems? Is that really true? Well, let me show you some that are a little different. Those first ones I was hoping you would all guess. What about this? Do you recognize this sequence of graphs? Sorry, these are graphs in the other sense now. I'm plotting points. These are the complex roots of a family of polynomials. And this, I claim, is as close, this should be your best friend. This is your second best friend, actually. Where the roots of unity are your first friend. What is this?